My name is Gisela. I don't know if you have someone outside Unicidi, but it's a pleasure to present Professor Judth Bosmans from the Department of Health Science at the FU Amsterdam, where she's ahead of the Health Technology Assessment section. Judith, today you talk about economic evaluations, the problems with real data, real world data, and how we can deal with these problems presented preliminary results from your research. Judith, thanks so much for accepting our invitation. Yeah, to be here today. Yeah, thanks so much.
Thank you, Gisela. Welcome, everybody. Well, like Gisela said, my name is Judth Bosmans. I work at VU in Amsterdam. Actually, this is our campus that you see on the slide. Well, Christina and Gisela will recognize the campus, but maybe more of you are interested to come here, then please get in touch with us. So today I will be giving a lecture about cost effectiveness using real world data. If you have questions, please raise your hand or use your microphone to interrupt, because I think it's best to answer the questions at the point that they are occurring, because then probably the explanation makes more sense as well. So today, this is a brief overview of the talk that I will be giving. So I will give a brief introduction into economic evaluations. I have you on a different screen than my slides. So if I look to the side, and I'm looking at you, and if I'm looking into the camera, then I'm looking at the slides. So the first part will be an introduction into economic evaluations, then a bit about the design of economic evaluations. Why are we interested in doing economic evaluations using real world data? Then some challenges that we have encountered in the past, well, 6-7 years when using real world data to do cost effectiveness analysis. Some preliminary findings of from 2 of my PhD students. And I will wrap up with some conclusions. So first, economic evaluations. Well, I think it's good to start at the decision problem. So why do we need cost effectiveness analysis or economic evaluations? So as you will know, and it's the case in all countries, that the population is aging, and when people age, they need more healthcare. But there are also more and more new health technologies coming into the healthcare market. And then you can think about treatment possibilities like new expensive drugs, or maybe surgical robots, new ways to diagnose health conditions like advanced MRI scans or PET scans. So there are all kinds of new health technologies coming into the market. And what they have generally in common is that they are more expensive than the regular care that we offer right now, but they're also more expensive. So there's a big demand for healthcare services, both because of the aging of the population and the introduction of new health technologies. But the budgets that we have available to provide healthcare are limited. So we have to make choices. Which care are we going to reimburse? Are we going to implement in the standard care setting, and which ones not? And that's where economic evaluations can help us. Because in an economic evaluation, we do not look only at the effects, so the health benefits of new intervention, but also at the costs of these healthcare interventions. And we always make a comparison of 2 or more interventions. So the cost effectiveness of a new drug doesn't exist. It's always the cost effectiveness of that new drug drug in comparison to the standard of care that we are providing right now. And by giving this information, we actually provide information on the relative efficiency of the new healthcare intervention compared to the usual care that we provide. And you can, when you buy jeans or when you buy a house, you compare the characteristics of the jeans or the house, and you look at the price, and then you make, then you balance these against each other, and you make a choice which one you will buy, which jeans or which house. In healthcare, it's not so easy as that, because whether you need healthcare or not is not a choice, right? We do not choose to become sick and to need healthcare. So the prices that are used in healthcare are generally not a reflection of real scarcity. So that means that we cannot compare interventions based on their price alone, but that's why we do economic evaluations, where we look at the relative efficiency of the two treatment options that we have available. So in any economic evaluation, cost effectiveness analysis, whether it's based on trial-based data or real-world data, our final outcome measure of interest is the incremental cost effectiveness ratio, or the ICER. So in that ICER, we actually estimate the additional expenses that we have to make to gain 1 unit of health benefit extra. So we calculate it by subtracting the mean costs in the control group from the mean costs in the intervention group, and dividing that by the difference in health benefits, clinical effects between the two groups. And if the intervention is more expensive and more effective than the standard of care, then the ICER represents the investment you need to make to gain 1 unit of health effect extra. The problem with these ICERs, because it's a ratio, is that their interpretation is not very straightforward. So if you have a positive ICER, then it can be that the new intervention is more effective and more expensive than the usual care, but it's also possible that it's less effective and less expensive, because plus divided by plus is a plus value, but minus divided by minus is also a plus value. So we often use the cost effectiveness plane to show these ICERs. So in this plane, you can see that on the x-axis, we show the difference in effects, so the difference in health effects. And on the y-axis, we show the incremental costs, so the difference in costs between the two treatments. And then we end up with 4 quadrants. The green and the red quadrant are pretty straightforward. If the ICER value is in one of these quadrants, then your decision is pretty clear, because in the green quadrant, the southeast quadrant, your new intervention is more effective and less expensive than the old intervention and the standard of care. So in that case, your new intervention is better in all aspects. And we say it's dominant over the standard of care. If it's in the red quadrant, in the northwest quadrant, then the new intervention is more expensive and less effective than the standard of care. And in that case, we say that it's dominated by the standard of care. Does not provide any value for money. You have to invest more money, while the health effects that you gain with the intervention are less than with the standard of care. In the 2 blue quadrants, the decision is a bit more difficult, because in that case, in the northeast quadrant, your new intervention is more expensive and more effective than the standard of care. And in the southwest quadrant, the new intervention is less effective and less expensive than the standard of care. So in these 2 situations, we need to make some kind of a trade-off. In the northeast quadrant, we have to decide, are we willing to pay so much money extra to gain 1 unit of effect? And in the southwest quadrant, it's the other way around. We have to decide whether we're willing to trade off some health effects with the benefit that we save money, so that we spend less money on our healthcare system. So in both these cases, we have to make a trade-off. And we will talk a bit more about that later on, but I hope that you all have some experience with economic evaluations to at least grasp that concept properly. So when we're dealing with cost effectiveness data, there are some statistical challenges that you need to deal with. And I will not go in this scoping review. We identified 7 statistical challenges that you encounter when analyzing cost effectiveness data. I will not go into all of them, but there are 2 that are important to mention, I think. And the first one is that generally cost data are very highly skewed, and they're skewed to the right. So when we have cost data, what we often see is that there are only few participants, few patients will have very high costs, and the majority of patients, of participants in our trial has relatively low cost. So you will see that there is a tail towards the right end of the distribution. And the other thing with cost data is, of course, that you cannot have negative costs. So costs are always bounded at 0. So we have a very skewed distribution, which makes our statistical analysis more complicated, because generally we assume that our data are reasonably normally distributed. The other thing that you really have to take into account is that costs and effects are generally correlated. So, and it can be either positive or negative correlation, right? So it can be that people who have better health outcomes after the trial had more healthcare utilization, so that there was a lot of healthcare provided to these patients that have resulted in these better health outcomes. In that case, the costs are higher and the effects are higher, so you have positive correlation. But it's also possible that more healthcare resources are spent on the people who are not doing so well, who have worse health outcomes. And we do a lot, we provide a lot of health services to hopefully make them better. In that case, you have a strong negative correlation. But what we see in cost effectiveness data is that the correlation is often pretty strong. So you have to take that into account in the analysis of the data. And there's a solution that deals with both these challenges at the same time, and that's bootstrapping. So I'm not sure whether you've heard of bootstrapping, but basically it's a way to estimate statistical uncertainty without making any assumptions about the distribution of the data. So we can estimate statistical uncertainty without making the assumption that the data is normally distributed. But it also, because we bootstrap costs and effects in pairs, it also retains the correlation between costs and effects that we have observed. So in that sense, bootstrapping is the ideal solution. So within my group, we generally use bootstrapping to account for these 2 statistical challenges at the same time. So it's are most of you familiar with bootstrapping, or does it need a bit more explanation? No, it's good?
Yeah, that's good. You did.
Okay. And then you can present the statistical uncertainty using a cost effectiveness plane. So this is the cost effectiveness plane again, only we cut off the x-axis and the y-axis at 0. But what you see here is actually that there's a very strong correlation between costs and effects, because the cloud, the shape of the cloud goes from the top left corner to the bottom right corner of the CE plane. So the red dot in the middle is our point estimate of the ISR, of the incremental cost effectiveness ratio. And all the blue dots around the red point are the bootstrapped replications of our ISR value. So this represents the uncertainty that there is surrounding the ISR, the point estimate of the ISR. The next step is, of course, to decide, and that's where the blue quadrants come in, is our new intervention cost effective? Are we convinced that spending our resources on this new intervention is a good way, or actually the best way, to spend our resources? And the decision rule we have for that is actually pretty simple. So the ICER should be below the maximum amount of money that we are willing to pay to gain 1 unit of effect. And then we consider the intervention cost effective compared to the standard of care. So in this figure, you can see that. So we have the plane again, right? So this is again the cost effectiveness plane. And the diagonal green line is basically our willingness to pay threshold. So that's the maximum amount of money we're willing to pay to gain 1 QALY or 1 recovered patient, or which clinical outcome we're interested in at that point in time. Every ICER value that is below that green line, so that the green parts of the plane, are considered cost effective. And if the probability that our ICER value is in the green parts of the plane is high enough, then we can say that our new intervention is cost effective compared to the standard of care. Everything that is in the red parts of the plane is considered not cost effective. So far we only talked about the ICER, or I only talked about the ICER, but there's also an alternative for the ICER, and actually this is a reformulation of the ICER decision rule, but that's called the incremental net monetary benefit, and often we just say net monetary benefit. And basically what we do then is that we calculate the monetary value of our health benefits, and we subtract the costs from that monetary value of our health effects. So in this case, if net monetary benefit is greater than 0, so the value of our health effect in monetary units, whether that's euros or dollars, is larger than the investment that we need to make, then we consider the intervention cost effective compared to control. So here you can see a hypothetical example. We have an effect difference between the treatments of 2 QALYs. We have a cost difference of 40,000 euros, and our willingness to pay threshold is 50,000 euros per QALY gained. In that case, we calculate net monetary benefit as 2 times 50,000. So the monetary value of 2 QALYs is 100,000 euros in total, and we subtract the investment that we need to make, the 40,000 euros. So in this case, our net monetary benefit is 60,000 euros, and this is a cost-effective intervention. So I mentioned the net monetary benefit because one of in the preliminary findings that I will present to you later on, we will use net monetary benefit to assess the performance of the different methods. So net monetary benefit is an alternative to the ICER, and the advantage of using net monetary benefit is that you include the willingness to pay threshold in your calculation. So you can see right away whether your intervention is cost effective or not, because if the net monetary benefit is positive, then it's cost effective intervention. The problem is that we often do not know what is the most relevant value for willingness to pay. So what we do then is that we estimate cost effectiveness acceptability curves in which we plot the willingness to pay, the different values that are relevant for the willingness to pay threshold on the x-axis, and we plot probability that our intervention is cost effective compared to usual care on the y-axis. And basically what we do is that we estimate the proportion of bootstrapped cost effect pairs that's below a specific willingness to pay threshold. So if you want to know more on about the analysis of trial-based economic evaluations, I would like to refer you to this paper. So it's a tutorial paper in which we explain step by step how you can conduct a trial-based economic evaluation in R, but also explain the rationale behind some of the solutions that we came up with for the different statistical challenges in economic evaluations. So that was the brief introduction into economic evaluations. Are there any questions about that?
Judith,
No?
I
Yeah.
have two questions. Yeah, about the bootstrapping replications, how we can decide about the number of replications in a study? There is a recommendation, or you just need to think?
I would use at least 1,000. So when I started my PhD like 20 years ago, a bit more, I think, I'm afraid, 1,000 bootstraps took like 4 hours to do. But now with the computers we have now, we generally do 5,000 because they're fast enough. And you will see that if you do bootstrapping and you, for example, start with 100 bootstraps, then 500 and increase it, that with the first increases, you will gain a lot of uncertainty. So it will be more consistent. It will convene more. But after 3,000-4,000 bootstraps, you will see that the additional bootstraps do not have a high additional value. So we generally do 5,000, but it also depends a bit on how skewed the data is. If you have a small sample with very skewed distributions, then you might even want to do a bit more. But generally, 5,000 should be enough.
Okay, yeah, because you have some studies here with a small sample size, because yeah, you calculated the sample size based on effects, and just for the effects, for example, in the hospital, in general, we have 16 patients per group. That's for the effect, it's enough, but the distribution it's not so good for costs. Yeah, but you can do more than 5,000. It's I need to test this before and then see the distribution, and I can increase a little bit more about the replications. Yeah.
Yeah.
Thank you, Judith.
Did you have a second question or?
Yeah, the sample size. Yeah, it was the perfect because the question is you'd be about the sample size and a small sample size and the bootstrapping solution. Yeah, thank you.
Yeah, but it's a good point you mentioned, because generally, because the cost data are so skewed, we will not have sufficient power to test for significant differences in costs. And that's important to realize in economic evaluations, we focus much more on estimating uncertainty than hypothesis testing, because we generally do not have enough power to test our null hypothesis. So in economic evaluations, we generally focus on estimating the uncertainty and estimating the probability that our new intervention is cost effective compared to usual care at a specific willingness to pay threshold. And if that's high enough, and it doesn't necessarily have to be 95%, but in some situations, we may also say that if the probability is 80%, we're satisfied and we consider it a cost-effective intervention. Okay, then on to the design of economic evaluation. So the gold standard has been to use randomized controlled trials to also establish the cost effectiveness of a new intervention. So, and you know, the advantage of a randomized controlled trial is that the intervention is allocated randomly. So any observed or unobserved confounders are assumed to be equally distributed across the two treatment groups, which helps us a lot in making causal inferences. However, there are also some problems with this gold standard. And one of the most pressing ones when using a randomized controlled trial to estimate cost effectiveness is that the population that we select to participate in our randomized controlled trials is generally very highly selected. So we have a tendency to only select the most healthy subgroup of people. So people who do not have additional risk factors, who are very compliant to the treatment, who eat healthy, who exercise, who do not drink alcohol, do not use painkillers or other drugs. So we really select the population in which you would also expect the intervention to be at its highest effectiveness. Whereas, and there will probably be healthcare providers among you, the people you will see in your consulting room are generally not the healthiest people. They have high blood pressure, they do smoke, they do not exercise. These are the people you see in your consultation room. Whereas most randomized controlled trials are conducted among this much healthier group of people that maybe have the health condition that you're doing your intervention for, but otherwise are pretty healthy. So that means that the findings, the results that we obtain from our randomized controlled trial may not be representative of the population that you see in your consulting room. And actually in the Netherlands, there's a lot of evidence that, for example, the expensive cancer drugs that we now reimburse and that are in randomized controlled trials are concluded to be cost effective, are not cost effective at all when we reimburse them for regular patients, because they have so many additional health issues that we need to deal with. So that's very important to realize that if you conduct a randomized controlled trial, that it's important to not be very selective in the patients that you recruit into your trial. The second problem with randomized controlled trials is that generally the treatment protocols are very strictly prescribed. So it's very clear, if this happens, you have to do this. The patient gets this dosage of the new drug this many times per day. Whereas in actual clinical practice, it's a bit more loose, right? You see the patient, you consider what's good for that patient. Maybe it's a very thin patient, so you may want to reduce the dosage of the drug a bit. So in actual clinical practice, you're much more flexible in the treatment protocol that you provide to the patient. Whereas in randomized controlled trials, it's generally a one-way street, right? So this is the way you need to treat patients in the trial. And otherwise it's considered a protocol violation. That also means that in randomized controlled trials, co-interventions are generally not allowed. Whereas in actual clinical practice, if you provide a drug to your patient and the patient has a side effect, you will provide a co-intervention. So, and these co-interventions may also have an impact on the health outcomes and the costs of the patient. So it's important that if you want to estimate the cost effectiveness of the treatment in real life, that you also take into account these co-interventions. And finally, follow-up measurements. So in trials, we generally follow up patients much more intensively than you would do in actual clinical practice, because we really want to keep a close tab on what's happening to the patient. And of course you do that, right? Because you spent a lot of money on the randomized controlled trial. So you really want to know very precisely what's happening to the patient. But these are extra costs that you maybe wouldn't make in actual clinical practice. So it's very important to make a distinction between the actual care costs that you make and the costs that are related to the fact that you're conducting the randomized controlled clinical trial. And basically what it comes down to is that in randomized controlled clinical trials, we're generally interested in estimating the efficacy of the new intervention compared to the standard of care. So we want to know whether under strict circumstances in a strictly selected population, the new intervention works. Whereas for economic evaluations, for healthcare decision making, we're much more interested in effectiveness. So does the intervention also work, is also cost effective in our actual clinical daily setting? So that means we need to include patients that are representative of our actual population, patient population, that we have to provide the treatment according to the protocols, standards of care, guidelines that are in place in the setting where we provide the care, and that we do not want to include all kinds of extra assessments or diagnostic testing that you would do as part of a randomized controlled clinical trial. So to support decision makers, we're interested in effectiveness, the real world impact of the new intervention compared to the standard of care. And if you base your decisions on these strictly controlled, randomized controlled trials, then it may be that you make a wrong decision, so that you decide, I'm going to reimburse this new intervention because it's turned out to be cost effective in a randomized controlled trial, but in the actual clinical practice, it may turn out not to be cost effective at all. So basically what you have to do is make a balance between the level of evidence that you want to have on one side and the risk of bias and the external validity that you need to make a decision. So the randomized controlled trial in this figure is in the upper left corner. So we have a high level of evidence because of the randomization. So any effect that we find, we can attribute to the intervention that the patient received. But the external validity of the findings from a randomized controlled trial are often quite low because of these problems that I described just now. The risk of bias, however, is very low as well. So we have a high level of evidence because of the low risk of bias, but often low external validity. And a solution that there is to this problem is to conduct a pragmatic control trial. So then you conduct a randomized control trial. So you keep the distinguishing aspect, the randomization, which makes causal inference much easier, but you try to resemble actual clinical practice as much as possible in your trial. That means that you still have a reasonable level of evidence, that the risk of bias is also relatively low. The external validity is a bit higher, but still it may not be high enough to base decision making on. So that's where real world data come in. So we're collecting a lot of data, and we're trying to use that data more and more to also support healthcare decision making. The problem is generally with real world data that we have a high risk of bias and that the level of evidence of that type of data is relatively low. So we have to really adjust for the biases that exist in real world data to be able to support decision making. However, the big plus of using real world data, of course, is that the external validity, the generalizability of the data that we use is very high because we collected them in actual clinical practice. So we do not have to make attempts to resemble clinical practice. It is clinical practice. So that's the big advantage of using real world data. And like I said, there are so many types of real world data nowadays. So we have administrative claims records, for example, at healthcare insurers. You have electronic medical health records, but there may also be patient registries. So in the Netherlands, we have this network of hospitals that treat cancer patients, and they all collect, as a network, they collect all kinds of parameters and health outcomes on cancer patients. And you probably have these kinds of health registries in Brazil as well. There may be public health surveys. Here in the Netherlands, I'm still wearing a traditional watch, but more and more people are wearing smart watches that collect all kinds of health data during the day and night. Social media may provide relevant data. So there are all kinds of real world data that you could use for your actual economic evaluation. So it seems like a waste to not use them. However, there are also lots of challenges associated with using real world data. And one of the most important ones that we encountered in our research is the linkage of the different data sources. So in the Netherlands, the privacy laws are very strict. So you are not allowed to use the social security number to link data about patients. So it's very difficult to link these different types of data sources that we have available. And I know that in Brazil, it's, I think, a bit more more easily possible, but still it's very difficult there as well to link different data sources together. And in the Netherlands, it means that we need to have, and you can see that in the red square in the middle, we need to have a trusted third party that links the data, the different sources of data that we have. So we send the data to a trusted third party, they make the connection, they make the linkage, and then the data goes back to be used for analysis or quality assurance. So there's a third party in between. And we have to ask all people for informed consent to link their data to other sources and to use it for research. So that's one of the biggest problems that we encountered in the Netherlands. And that will be the case in the complete EU countries. The other thing is that there may be lots of types of data, but you are probably not able to use all types of data. So you have to make choices. Maybe it's possible to link hospital data, primary care data, and some health outcome data that you can collect from patients, but it's not possible to, for example, also link absenteeism data from paid work, or maybe healthcare insurance data or environmental data. So there's more and more evidence that the environment that we live in also influences our health. So it might also be interesting to use that kind of data. So there's a limited availability of the data that we can link to inform our cost effectiveness analysis. And sometimes it's not a problem, but sometimes if you expect a huge impact, so if you expect that people recover from their low back pain faster with new intervention than the old intervention, then there may be a big impact on healthcare or work absenteeism. If that's the case, then it's rather problematic if you do not have data on work absenteeism in your data set. So it's trade-off between completeness of data and the availability of the data. And I see that I forgot to change the title of this slide, but another problem is that it's also hard to identify different treatments within the data. So we had availability of a big data set from a mental health care institution. And what you see here in the right top corner is a figure in which is shown how many patients received all these different types of health services within that sample. So that it were, I think, 90,000, 95,000 patients with depression, and each bar is a patient. So you can see that lots of patients, for example, used supportive structuring therapy. And there were lots of patients that used activation therapy. But it's very difficult to classify different treatments based on these kinds of data. So in the end, what we did is that we made combinations of different types of care data. So all the sort of 1.1, 1.2, 1.3 are all different treatment types that we identified, which are actually packages of different interventions that you can provide to patients with depression within the mental health care setting. And these 9 columns are the different treatments that we distinguished within the data. But it can be very complicated to do that if you have real world data. If it's about whether patients received a specific drug or not, then it's more easy. But in settings like the mental health care setting, it can be rather complicated to identify patients who did or did not receive the treatment that you're interested in. So these are the more pragmatic challenges that we identified, but there are also lots of methodological challenges that you encounter when analyzing real-world cost-effectiveness data. And I think the most important one is actually confounding. So this is a very well-known example where we have a treatment, which is a hospital admission, and the outcome mortality. And probably you will find that people who have a hospital admission are more likely to die than people who do not have a hospital admission. Does that then mean that being admitted to the hospital increases mortality? No, right? We admit people to the hospital to make them better. So probably there's some confounding factor. Oh, I'm sorry. I made slides yesterday. This should be confounding and underlying health conditions. But there is a reason, of course, why people are admitted to the hospital. They have an underlying health condition that made it necessary for them to be admitted to the hospital. And because they have that underlying health condition, they are probably also more likely to die than their more healthy counterparts in the population. So hospital admissions do not increase mortality, but there's some underlying factor, a confounder, the underlying health conditions, that influences both the fact that people need a hospital admission and the outcome that we're interested in, namely mortality. So the underlying health conditions modify, bias the relationship between hospital admissions and mortality. If you do not take into account that confounder, then you make very wrong conclusions, right? And we should close all hospitals, which does not seem to be a good solution to the problem. So you really have to deal with confounding. The second problem that you often encounter within real world data is that there are missing values. So these can be occasional missing values, but it can also be that the values are missing by design. So for example, in the Netherlands, I already said we used mental health care data. And in the Netherlands, we have something that we call routine outcome measurements. So at set points in time, the condition, the well-being of the patient is being measured. And that was done up until 2017 very regularly. So every 6 months, every patient had to fill out some questionnaires about the mental health status of the patient. However, after 2017, that was not mandatory anymore. So then you can see that there's lots of missing data, monotone missing data, but that's missing data by design. So you probably know what happens in your country. You know whether there are policy decisions that may result in additional missing data, so you can account for that. The occasional missing values, however, are more problematic. So if they're missing completely at random, so for example, the lab technician drops the tube of blood that you just gave for a lab test, then we say it's missing completely at random. It's a completely random process. The lab technician didn't choose which lab tube he or she would drop. So there's no association with the actual health status of the patient or other characteristics of the patients that result in the missingness of data. However, what we often see is that we have data that is missing at random. So we have missing data, but we can link that or associate that with some of the characteristics that we measured. So what we see a lot is that older people do not fill out follow-up measurements because they're too tired, or it's too how do you say that? Too severe for them to do, too hard to complete the questionnaires. In that case, we have missingness, but we know which characteristic of the patient is associated with that missingness, and we can use that to impute the missing values. However, it's also possible that we have data that's missing not at random. In that case, the missingness, so we have a missing value on one of our outcomes, but the missingness is actually related to the value of that outcome measure, so the value that we did not observe. So for example, often it's the case that patients who do not do very well drop out of the study. And maybe if you're doing a study in depression, the people who are admitted to a psychiatric hospital because their depression is so severe will not fill out questionnaires. In that case, the missingness is related to the outcome of the study, but you did not observe that outcome. So it's very hard to adjust for that. So when you have indications that your data is missing not at random, and that's often the case in real world data, you have to be more careful with the conclusions that you draw based on the analysis that you did. Are there any questions? I think I saw one coming into the chat. Is that correct?
It's from Monica, Professor Monica. Yeah, she's here. Monica?
Yeah. Hi, Judith. How are you?
Hi. Good.
Yeah, I was just commenting because we have a very large country with substantial differences between the regions. Of course, the public system have payments that are cross-cutting, but people needs are quite different, and probably the out-of-pocket expenses are really different. So when we are talking about a pragmatic study, at the country level, perhaps we will need a multi-center study. So it's a very expensive study as well. Do you have any comment on that?
Generally, I would say it depends a bit where the decision-making is happening, at which level. So for the Netherlands, where all decision-making about reimbursement of healthcare is done at the national level, I would say you always need a multi-center trial because there are big differences between, for example, Amsterdam or the more rural areas in the north of the Netherlands or the south of the Netherlands. So you would like to take into account these regional differences as well. So for Brazil, I would say if it's about national healthcare decisions, it would be good to have all regions included in the trial. If it's at a more regional level, I would still say, because the regions are so big in Brazil as well, that there probably are big differences within regions as well. So even then, I would say that a multi-center trial is generally preferable over a single center trial.
Yeah.
And that's probably more feasible if you use real world data, because then the data collection is much less expensive. There's a lot of effort involved in the analysis of the data.
Yeah, sure. I was also thinking that, as you said, also at the state level, we have different municipalities with different sizes, for instance, as well. So living in a very cosmopolitan city as São Paulo is quite different from living in a small city. So probably we will have differences as well. So I was thinking that pragmatic studies is so difficult to conduct because we have major issues related to, sampling and finding, the people that are really entitled to be there in the pragmatic clinical trials. So yeah, but you are right. I totally agree with you that if you want to say something that is going to be transferred to a practical level, we are right. Yes.
Yeah, and I mean, it will not always be possible to do a multi-center trial, but then it's very important to look at what are the differences between different regions, different municipalities, and can you expect that these differences affect the decision or the cost effectiveness of the intervention?
Yeah.
But it's hard. But generally, I would say if you want to support decision making, you need a multi-center trial in all cases. Yeah. Are there any other questions?
I think no, you just a comment. Yeah, because here we have there is some data available from the SUS for the Brazilian public health, but for me, the most difficult thing it's to cross the variables because probably we have our outcomes, clinical outcomes in a data set and the economic outcomes in other one. But it's difficult to identify the same patients in each data set.
Yeah.
How can you deal with this in the Netherlands? Yeah, because
in the Netherlands we use the trusted third party to do that. So generally, they have to adhere to very strict regulations, and they can have the social security number. So they have different data sets with the social security number of the participants. They link the data. They then make the data anonymous, and then it goes back to the different data providers for analysis or reporting. So that's how we do it in the Netherlands. But I know that you have less strict rules. So then you have to match on, for example, age and postal code, but that's sometimes very difficult.
Yeah, because we did not have a number or ID for patients.
Yeah.
And in my idea, yeah, you can identify patients for cities and the same age for many other personal data, I think so. Yeah, but it's difficult.
Yeah, but the mental health care data set that I was talking about, there we had 95,000 people in there, and we could, based on the data that we had, we could identify 99% of the patients uniquely. So it's difficult, but if you have sufficient data, you can really identify lots of patients uniquely. Yeah. And that's at the same time the problem, right? Because then it's really difficult to maintain anonymity of participants or citizens.
Okay. Are you using some artificial intelligence to identify patients in different
not so much yet. What we do use is that we use the observed data set and create synthetical data based on the actual data. So we create fake data based on the observed data, and we use that to at least to develop our analysis tools, so we can, for example, what we did in one of the studies is that we developed analysis scripts based on the synthetic data, and then put the analysis scripts on the servers of the where the data was stored, did the analysis, and only retrieved the aggregated results.
Okay, thank you, Judith.
Yeah. Any other questions? No, so then I would like to present some of the some fresh off the press preliminary findings. So this is from the work of two of my PhD students. One of them, Anita Varga, will defend her thesis this Tuesday. So we're very excited about that. And she mainly focused in her PhD thesis on dealing with confounding in observational or real world data. So this is a scoping review that she wrote, in which she went through 128,000 papers to end up with 127 papers of simulation studies that evaluate the performance of different methods to deal with confounding. And when we talk about confounding, we have two types of confounding. So we have measured confounding, which is confounding that's caused by variables, characteristics that we observed or measured in our data set, and unmeasured confounding, which are factors that we did not observe. So if we look at measured confounding, then based on the scoping review that Anita did, propensity score methods seem to be the most appropriate method to deal with confounding. So basically what you do is that you estimate the propensity score, which reflects the probability that the participant receives the intervention under study. And that probability is based on the characteristics of the patients. So you actually predict how probable it is that the patient received the intervention. And it's important to realize that that not may be the intervention that the patient actually received, right? So it's just based on the data that we observed, what is the probability of receiving the intervention? And then you have different methods that you can use. So you can adjust for the propensity score in a general linear regression model. You can match patients based on these propensity scores, or you can stratify based on propensity scores. For unmeasured confounding, the most the methods with the highest performance were instrumental variables and a difference in differences. So with instrumental variables, you have to have an instrument that influences the health outcomes. So for example, in Europe, a well-known instrument that we use to estimate the association between in-uterus health conditions and outcomes later in life is the last winter of the Second World War. Then there was a very cold winter in Europe, and there were lots of children also born during that winter, but we used that winter as an instrument to estimate the impact of uterus conditions on later health outcomes, such as cardiovascular mortality at the age of 70. So that's it's a variable, and a characteristic, a factor that you can use to actually mimic the intervention, because you cannot say, okay, this woman will get very low nutritious foods and hard circumstances, and that pregnant woman not. You cannot randomize something like that. So it's generally a factor that you can use to mimic the effect of an intervention. Within differences, we actually try to model what would happen if someone would not have received the intervention, or if someone would have received the intervention. So we use the trend, and if you want to conduct difference in difference analysis, you have to have quite a lot of longitudinal data, because we look at the trend in the outcomes that the patient has in the two intervention groups, and we try to model what would have happened if the patient would not or would have received the intervention. So you need quite a lot of data to conduct a difference in difference analysis. So these were the methods that we found most evidence for. It's very important to realize that in this scoping review, we only included simulation studies, because in simulation studies, you know what the true outcome is. So you can really quantify the performance of the different methods. However, there are many more other methods available that were not tested in simulation studies that we did not include. And you will see that in the next study as well, that there are some methods that we assessed that did not come up from the review we conducted. When you use propensity score methods, it's very important that the propensity score model that you use, so the model you use to estimate the propensity scores, that's properly specified. Because if you misspecify that model, then your outcomes are very heavily biased, and it can be disastrous if you misspecify your propensity score model. For each of the methods, so they result in different estimates, so different statistical outcome measures, the different methods. So it's very important to decide beforehand on what is the estimate that is of interest to your specific decision problem. And generally, that's the average treatment effect for the total population. But sometimes it's different, and then different methods result in different estimates. So it's very important to decide beforehand about the estimate, and also link your choice of method to that specific choice. And finally, it's important to consider the plausibility of the assumptions that the different methods require. So for example, for the difference in difference methods, it's very important that you have longitudinal data, and that there are also trends to be identified within the different treatment groups in the data that you have, because otherwise you cannot do the analysis. And in the scoping review, we describe lots of these assumptions in more detail. So when we did that scoping review, and then the next step actually was to see what the performance of the different methods that we identified to deal with measured confounding was in real world cost effectiveness data. So what we did is that we used the mental health care data that I mentioned earlier to simulate data on which we could test the performance of the different methods. So we compared 5 new methods. So the seemingly unrelated regression, the SIR, the blue squares, that's the traditional method that we use. And we compared this traditional method to 5 other methods. And what you can see is on the x-axis, you can see increasing levels of confounding. So K1 is a low level of confounding, and K3 is a high level of confounding. And what you can see is that for all methods, as the level of confounding increases, the bias of the outcomes increases for all methods as the level of confounding increases. So you can see that the relative bias, which is the proportion of deviation of the obtained outcomes from the true value. So that's the percentage of deviation from true value. So that should be as close to 0 as possible, of course, because then there's no deviation. And you can see that the higher the level of confounding is, the more bias there is, the larger the distance from the zero line becomes. And actually, what we saw in consistently over all scenarios that we analyzed is that both genetic matching and targeted maximum likelihood expectation methods performed best. The genetic matching is very computer intensive, so they take a long time, these analysis, especially if you have large data sets, which is often the case with real world data. So basically, we're now testing the TMLE in an empirical data set, because that's, well, the bias is relatively limited with the TMLE, and it's also not so intensive that it's almost infeasible to conduct the analysis using TMLE. And this was for a treatment ratio of 0.2, so 20% of the patients or participants in this data set received the intervention treatment, but we saw the same picture for higher treatment ratios. It's also possible that you have time-dependent confounding. So this first study was about measured confounding at one time point, but it's also possible that the confounding differs over time. So here we have a simplified example of that. So in this case, we have treatment A0, which is the treatment at time point T0. This treatment is influenced by a confounder, L0. So for example, the age of the patient or the severity of the health condition may influence the type of treatment that a patient receives at baseline, at time 0. However, this treatment may affect the value of this confounder. So age probably does not, treatment does not affect age. So that's not a good example of a confounder. But for example, the severity of the health complaints are probably affected by the treatment that you give the patient. So the value of the confounder at time point 1, L1, may be influenced by the treatment. And if that's the case, that may also influence the treatment that the patient receives at time point 1. Because if the symptoms get better, so disappear, then probably the physician makes the choice to stop the treatment or to provide a milder treatment to the patient. So the treatment that the patient receives at time point 1 may be influenced by the change in the confounder. Well, you can already see that if you do not adjust for that, it may become pretty biased, the outcomes that you have, right? So the outcome that you observe is not only the result of the treatment that the patient got at time point T0, but also the change in the confounder that you know that is influencing the treatment and the outcome, but that may have also influenced the treatment that the patient received at time point 1. So it's very important to also adjust for that. And in real world data, you very often see this, because if a patient improves, you will change your treatment. So in the second study, second simulation study that Anita did, she used the same simulation setup. So she used again the mental health care data to simulate data and a real world data set. And what you see here is that again, the TMLE performed rather well if you look at the bias that exists in the outcomes. So for all levels of confounding, A, B, and C, so A is the lowest level of confounding and C is the highest level of confounding, the TMLE did pretty well, but also the G computation performed rather well. Again, the G computation is a very intensive analysis method. So generally, I would recommend to do the TMLE. also because it performs so well with the measured confounding. And the marginal structural models, you can see that they have quite a lot of bias, right? So they, in all three scenarios, the bias is largest for the marginal structural models. And we saw that across all scenarios that we analyzed. This picture came out for all different scenarios that we evaluated. Then the second PhD, who submits her thesis to the committee, hopefully early next week, who is actually from Honduras, so pretty close to Brazil. She looked at missing data in real-world data. So depending on whether you have data that's missing at random or missing not at random, you have to use different methods. So for the missing at random, generally the multiple imputation methods perform best. And both multiple imputation by chained equations and multivariate normal imputation came up as promising methods to impute missing data according to a MAR mechanism in real-world data. For data that is missing not at random, pattern mixture models or sample selection models perform better. So in pattern mixture models, you actually model the difference in the distributions between missing and observed values. So, and you try to group observations based on their missing data pattern. And then per missing data pattern, you specify a missing data model. So it's very, it's actually quite complicated to do these analysis. But because missing not at random data in real world data is very often present, it might make sense to do a sensitivity analysis with either pattern mixture models or sample selection models. And in sample selection models, you estimate you try to model the mechanism by which data is selected. So by which the data is missing. So you try to model the underlying missing data mechanism. So again, you have to have quite a lot of data to do that, but it's also very complicated because you have to specify two models, an outcome model and a model to actually model the missing data mechanism. And then you link them through correlated error terms. So it's a pretty complicated type of analysis. So what we did in the other studies that Alejandra performed is that we looked at the performance of multiple imputation methods in real-world data sets that had data that was missing at random. So again, we used the mental health care data to generate simulated data sets, and we created the missings ourselves. So we knew what the missing data mechanism was. And then we compared complete case analysis to 3 different types of multiple imputation methods. So we used the mice PMM. So then we use predictive mean matching to impute the missing data, which is actually, if you have a case with missing data, you try to find similar cases. So cases with similar characteristics, and you randomly draw an observed value from one of these generally 5 cases that are similar to your case with missing data, with a missing observation. And you impute that missing observation. The other one, mice card, there you make regression trees. So, and depending on where the patient ends up in the regression tree, that determines the value that you impute for that patient. And we compared that to multivariate normal imputation. And what you can see is that, so the 15%, 35%, 55% are the different rates of missing data, so 15% of missing data, 35% of missing data, or 55% of missing data, what you can see is that basically all methods went wrong with very high levels of missing data. The relative bias became more and more pronounced. But you can also see that with higher levels of confounding, so on the x-axis, low, medium, and high refers to the level of confounding, that with high levels of confounding and high levels of missing data, the two balanced out against each other. So the bias became smaller again. So actually, if you have very high levels of confounding and very high rates of missing data, then they may balance out against each other. Although you do not know whether in other settings in actual empirical data, that's the same. But that's what we observed in our simulation studies. And in all scenarios, all cases, you see that the complete case analysis performs rather badly. So please, whatever you do not do complete case analysis, but choose one of the multiple imputation methods that are around. And probably the MySCART and the MVNI are the best performing methods to use. Then in the second study she did, we looked at missing observations in multi-level data. So what we had here was a completely observed Danish data set in which we created missing values. And again, we used 15%, 35%, 55% of missing data. And what you can see here is the cost effectiveness acceptability curves for each of these scenarios and for each of the different methods. And again, the red line is the complete case analysis. You can see that that's way off the others, right? So the multiple imputation methods seem to be close together. And we compare different scenarios here. So in this scenario, there were only missing data in individual level variables. So you may have patients that are clustered in hospitals. Then we have individual level variables, which is, for example, age and sex of the patient. And we may have hospital level variables. So, for example, whether it's secondary or tertiary hospital, what the size of the catchment area is, well, all kinds of different variables that are cluster level variables. So we simulated the scenario where there were only missing data in the individual level variables. And you can see that the complete case analysis is quite a way off from the actual, the complete data. So is it light green? The brown greenish, the second one in the legend of the figures. That's the true value based on the observed data. And you can see that the complete case analysis is farthest from the actual observed data, but that all three multi-level methods performed reasonably well, multiple imputation methods. And then in the second scenario, we had missing data in both individual and cluster level variables. And in that scenario, we saw that multiple imputation methods that also take into account the multi-level structure of the data performed better than the multiple imputation methods that do not take the multi-level structure of the data into account. So if you have multi-level data and you have missing observations at both the individual and the cluster level, then it's really important to also account for the multi-level structure of the data in your imputation procedure. Yeah, and you can see that here. So for the individual level variable missing data, you can use the single level multiple imputation methods. but for the case where we have individual and cluster level variables missing, you can either use the multiple imputation with a dummy indicator for the cluster that the participant is in, or you can use the multi-level multiple imputation by chained equations method, which is implemented in R in a specific package. So these are the findings we had so far with evaluating the performance of methods in real-world data cost-effectiveness analysis. Are there questions about that?
Anyone?
No? No?
Yeah.
Yeah.
Carol?
I'm sorry. I just started the master's degree, and I don't know a lot of stuff. But one thing that I didn't understand very well is about the population selection and the co-founders related to co-interventions, because when we do RCT, our population needs to be homogeneous, and that's not the real world.
Yeah.
That's my first question. The consort says that we have to have a homogeneous population, and how to manage this, because it's a conflict, right?
Yeah, so the consort statement does not say that you have to have only angels in your population. But they do say that you have to really well describe your population. So especially when you are less strict in your inclusion criteria, it's very important to describe the population that you included in your trial. But I think the most important thing to remember is what's the purpose that you want to serve with this analysis. Do you want to inform decision making? Then you really have to make sure that the setting that you include in your trial is also representative of the actual decision-making setting. If you're really interested in efficacy, so in establishing whether this new treatment works in a very highly selected group of people, then it's okay to use a selected group of people. So it also depends on the stage in which your intervention is. So in phase 2 trials of drugs, you do not want to do an effectiveness trial, then you really are interested in efficacy only. Whereas if it's a phase 4 trial, then probably effectiveness becomes more important.
Okay.
Does that answer your question?
Yes, you did. Thank you.
Are there other questions?
No, it's just a comment. It is so complex, this type of analysis, Judith.
Yes.
Are you planning to do something like a master class after Anita and Ale finished the PhDs?
Yeah, so we're now submitting the papers. So all papers also have the R scripts that we use in there. And we try to really explain what we did and how we did it. But it's very complicated. So I would advise you to involve someone with more experience in these analysis. Because also with Anita, she's an econometrician, so she has a lot of experience with using these advanced methods. Whereas for us health scientists, it's sometimes, whoa, what's happening here? Yeah. But we, with the papers that we're preparing now, that we are submitting now, all papers have all our scripts included.
Yeah, nice.
Yeah.
Thank you.
Okay, so then some conclusions. So if you look in PubMed, there's a huge increase in real-world data papers. So I did a quick search yesterday evening, real world evidence or real world data in the title of the paper. And then you can see that there's a really steep increase in papers over the last years. But it's also important to realize that although real world evidence is very important to inform decision making, that decision making is rarely based on one study only, right? So often we have a RCT, then the intervention is implemented in standard care. We have all kinds of data about the real world implementation of that intervention, and then we can analyze the cost effectiveness of the intervention in actual clinical practice. So often it's an ongoing process, right? It's a life cycle. We have data, we collect more data in actual clinical practice, and we get more and more evidence about the cost effectiveness of the new intervention. So I think randomized controlled trials are still very important, but in some cases they can be complemented by real world data, and sometimes maybe it's not possible to conduct a randomized control trial, and then you have to rely on real world data to make a decision. But then it's even more important to properly account for all these methodological challenges in the data that we see. And also it's important that real world data studies are very important inputs for health economic models. So for example, if you have preventive interventions or you have many different treatment combinations that you can use for a specific health condition, and then we rely on modeling, and especially then real world data studies are very important inputs, right? Because we want to model the long-term effects of treatments. And then real-world data studies can provide very important, very valuable information to populate parameters in these health economic models. And also they can help identify knowledge gaps. So maybe we see when we implement an intervention in actual clinical practice that are specific patient groups who respond especially well to the treatment, or that there are patient groups who do not respond at all to the intervention. So if we have real world data and if we analyze them properly, we can also identify these kinds of knowledge gaps or subgroups within a total patient population that the intervention is more effective in. However, it is important to realize that because we do not have the randomization in real world data, that you have to be very careful with claiming causality if you conduct a real world data study. And this was a recent review where they looked at observational studies, and the causality claims that were made, the causal language that was used in these studies. And they showed that of the 60 studies that they included, almost half used language that suggested that there was a causal relation between the treatment and the outcome. But you have to be really careful about that if you do not have an experimental treatment setup. So be aware of that. And as finally, like I just said, it's also very important to work together, to work between different disciplines. So in the project that the papers came from that I reviewed, or that I briefly touched upon just now, we worked with epidemiologists and econometricians, and we realized that there's a huge gap in the language that we use in both disciplines, but that we really need both disciplines to really make progress in the analysis of real world data. So I would advise you, if you want to analyze the cost effectiveness of an intervention using real world data, that you look for collaboration with, for example, econometricians, but that you also realize that there may be huge language differences between the disciplines that you need to resolve first before you can conduct a trial. So that is what I wanted to tell you today. So if there are any remaining questions, please let me know. And you can always get in touch with me as well through email. Are there any other questions?
Questions? Thanks so much, Judith, for today. Yeah, I think many students had some ideas. Yeah, I have we have some students probably will go to Amsterdam to learn with you about cost effectiveness analysis, but I think real world data is a challenge for us now. But this week we had a congress about health technology assessment in Brazil, and there were many presentations using real world data. Yeah, with different disease, but not specifically for physical therapy field. But probably I think in the next years, yeah, you increase this type of study here. I think it's important to learn about that. Yeah, maybe, yeah. Next years, probably you can see us in Amsterdam again without lockdown, please.
Yes, that would be nice.
Yeah, but you can come here next year. It will be very nice to have you here in person. And it just for discuss more about modeling and the real world data. Maybe you have more experience and new ideas about this type of study. Yeah, it'll be very nice. You are so excited, but FAPES it's always this way, you know. You just have your answer in the day of the, the event or the congress. Yeah, but you got the most difficult thing you got. Yeah, and then probably you can change the data, the date, sorry. But yeah, probably you can come here next year. Yeah, someone has a comment? Yeah, no. Yeah, people so shy. Yeah, like me. Yeah. So Judith, yeah, I can close. Candy, Rafa.
Yes, you can. I'd like to thank especially dear Judith and Gisela for the indication, for the suggestion, and you can finish.
Yes, thank you so much.
Well, thank you. Good luck.
And see you next year, Judith.
Yes, I will see you next year. I will share the slides with you, so you can share them with
of course.
Yeah, please.
Participants. Yeah.
Thank you so much, Judith.
To take the studies. Yeah.
Yeah.
For sure.
Thank you so much for your time, Judith. Have a good weekend. Yeah, for you.
You too. Almost weekend here, so
yeah, that's here for
Friday.
Okay.
Bye bye.
Thanks, Judith.
Bye bye.
Bye bye.
Bye bye.
You.